Hi, I'm Professor Sabrina Stierwalt, and I'm in the physics department here at Oxy. And I am an extragalactic astrophysicist, which means I study things outside of our own galaxy, out in the universe. So today I want to talk to you about some of the projects that we're working on this summer in the OGG, the Oxy Galaxy Group. So let's take a look at what happens when galaxies collide. I do want to start by saying a little bit about what motivates me to study the universe, and that is that the more I look out, the more it reminds me of our shared humanity. So we are all sitting here together on this rock that's hurtling through space at something like 67,000 miles per hour. And we're going around our star, the sun, which is very special to us, but it's only one of about 100 billion stars in our galaxy, the Milky Way. And our Milky Way galaxy is just one of something like 100 billion galaxies, many of which are still waiting to be discovered. And so when I look out and I study the universe, it reminds me that we're all in this together, and that our knowledge, that knowledge of the universe and where we come from, is something that belongs to all of us. So I mentioned we live in the Milky Way. This is a fairly massive galaxy as far as galaxies go. And we think it looks like this. We think it looks like a spiral galaxy. So we think we know how galaxies like the Milky Way form. We run simulations. So we can't watch it happen in real time because it takes billions of years. So instead we have to run simulations on computers. And so here's a picture of one of them, one of the highest resolution simulations that we have. And what we think happens is that smaller galaxies merge together to form larger ones. And so this is, in this image here, the massive galaxy, like our Milky Way, would be the brightest blob at the center. And then all of these little ones are galaxies that are coming together to merge into this bigger system. Now, these little ones are what I'm going to focus on for the rest of the talk. We think that when a bigger galaxy forms from the merging together of smaller ones, it's something like a Cookie Monster effect. So this galaxy is gobbling up all the small ones in order to grow its size, but there's a lot of crumbs that are left over. And so we can make observations of what galaxies look like today and see if the crumbs that we observe match what our simulations say should be there. And in fact, we do see our galaxy cannibalizing a smaller galaxy right now. So the Milky Way is eating something called the Canis Dwarf. And so here is a artist's rendering somewhat of what this looks like. So this dwarf is this stream. The smaller galaxy is being pulled apart because it's gotten too close to the Milky Way, and the stronger gravity of the Milky Way is winning and it's pulling it apart. So we call these smaller galaxies dwarf galaxies, as I've been doing. And so we think massive galaxies like our Milky Way form when these small galaxies interact with each other and then eventually merge. And we've found nice examples of dwarf galaxies merging out in the universe. Here I'm showing a picture of some of the better known ones. But we don't actually know how representative these examples are. We found these examples somewhat by accident. And so when we observe something out in the universe, we can't automatically know, okay, just because this pair of dwarf galaxies is merging and doing its thing in this certain way, that means every time a pair of dwarf galaxies merges, it's also going to do it in the same way. So we don't know if these examples that we find are actually representative of the larger class of dwarf galaxy mergers. And so that's where my work comes in. So I lead a group, we call ourselves the Tiny Titans, or TNT, and so we're doing a systematic study of interacting and eventually merging dwarf galaxies. And so what that means is that we combed the nearby universe for all of the interacting dwarf galaxies that we could find. So now we can make bigger, more statistical statements about the physics that goes on when dwarf galaxies merge together. So very briefly, just some of the questions we're looking at this summer with Tiny Titans. First is, are these cosmological simulations getting their dwarf galaxy predictions right? So that picture we saw in the beginning, We want to compare what we can observe today and see if those simulations are on the right track. So simulations predict, this is a major prediction from these simulations, that groups of only dwarf galaxies should exist, only the little guys. So this should make some sense, right? Before you get a massive galaxy, before all the little guys merge together to form a massive galaxy, you would find just little guys, little dwarf galaxies hanging out before the major massive galaxy has formed. This seems pretty straightforward, but we actually had never found groups of dwarf galaxies hanging out without a massive galaxy. So we hadn't caught that process in the act before the massive galaxy had formed. Well, Tiny Titans was the first to find these groups of dwarf galaxies. So what we did was we looked around our interacting dwarf galaxy pairs, and we looked for other nearby neighbors, and we found 7, we call them isolated groups because there's no massive galaxy around yet. And so here's a picture of one of them where I've highlighted the little dwarf galaxies for you. And so this was very exciting. It's a really nice test of those cosmological simulations, and it was just cool because we'd never seen these kinds of things before. But you may remember from that simulation that there were a lot of little things hanging around that massive galaxy, and not just these, something like 5. And so this is something that David is looking at this summer, which is if we push down to slightly fainter galaxies, so we get deeper imaging than what we started with when we originally found these groups, can we find more dwarf galaxies that are members of this group? So can we better match with the simulations and see if the simulations are getting it right by looking for more and more of these crumbs, these Cookie Monster crumbs. So David is doing that this summer by looking at a very specific plot that will help us pick out potential members of these dwarf galaxy groups. Another question we're asking is, do dwarf galaxy mergers trigger the growth of black holes? So our galaxy, the Milky Way, has a supermassive black hole. Supermassive is the official term. It means something like 1,000,000 times the mass of the sun, hanging out in the center. And actually, every big galaxy we look in, we find a supermassive black hole at the center. But we actually don't know how they're formed, despite the fact that we find them everywhere. So we find small black holes. So we call these stellar black holes, and we know very well how these are formed. So this is something like 10 times the mass of the sun. We get these from massive stars dying. And then we find these supermassive black holes in the center of galaxies. But we don't find much in between, what we call this intermediate mass black hole regime. So we have 2 mysteries here. How do supermassive black holes form? And why don't we find intermediate mass black holes? Are we not looking the right way? Are we not looking in the right places? Do they just not exist? Are they hard to find? And so we think these 2 mysteries are actually linked. And maybe if we know more about intermediate mass black holes and the masses they have and how frequently they exist or don't exist, then we might be able to solve this supermassive black hole mystery. So this is something that Olivia is working on this summer. So we know that when massive galaxies like our Milky Way merge with other massive galaxies, so our Milky Way will eventually merge with Andromeda, a nearby galaxy, that can trigger something called an active black hole. So black holes are very hard to find on their own. If you want to know more about that, you can ask Olivia. But we can find them indirectly from emission around the black hole. And that emission gets heated up and more excited through galaxy mergers. So we think we have a good shot at finding these intermediate mass black holes in these dwarf galaxies that are undergoing interactions and mergers. And so that's what Olivia is doing, seeing if we can find these elusive intermediate mass black holes. And then finally, a third question that we're looking at this summer is, why do superstar clusters keep popping up in dwarf galaxies? So our sun hangs out by itself, but most stars like to hang out in groups with their friends. We call them star clusters. And we expect that bigger galaxies can have bigger star clusters. So it makes sense, right? You're a bigger galaxy, you have stronger gravity, you're able to make bigger structures. So here is a plot where the x-axis is a proxy for for galaxy size. So as you go to the right, you get bigger galaxies. And the y-axis is a proxy for cluster size. So this is looking at the biggest cluster that sits in that galaxy. So we expect bigger galaxies to be able to host larger star clusters, and so we see that most do, right? These black points fall along a nice linear relationship. But then there are these red points that sit way above the line. That means they have unusually large star clusters in them, clusters that are so large they have no business having them because the galaxies themselves are quite small. And so we want to understand why these exist. This worries us a lot because we think we understand star formation and how star clusters form, but then if you throw in these things that don't quite fit what we expect, we get worried that we're not getting it quite right. What's going on here? And so that's something that Tarima's working on this summer. She's looking at images from the Hubble Space Telescope and studying the ages and the masses of these star clusters that we find in our interacting dwarf galaxies. Because we have a theory that the dwarf galaxies that have these unusually large star clusters, they may get those superstar clusters, as they're called, through interactions and mergers with other dwarfs. So that's what we're trying to track down. So thank you, and if you're interested in anything that you heard in this talk, how you form stellar mass black holes, what happens when galaxies collide, I suggest you take Physics 162, or this is the astronomy class that I teach for non-science majors mostly. And so we look at questions like, will the sun explode? What's the difference between astronomy and astrology? And could we deflect an approaching asteroid if we needed to? Thank you very much.